So before we begin deriving our equation, I want to take about a few minutes to remind you guys of the lab activity that we spent the last few days working on. So if you guys remember, we watched this video of this man standing on this ladder here, and he dropped a ball from near the top of the ceiling down near to the bottom. And remember, as the ball fell, remember the ball started off somewhere around here, around this mark, and we watched the video as the ball fall frame by frame by frame, and it ended up somewhere around here. Okay, so the distance from here to here represented the displacement of the ball. If you guys remember, we analyzed the data in Google Sheets, and we actually plotted out a velocity time graph for this data that looked at something like this. Okay, so remember this. So this is a velocity versus time graph, and this represents the negative end of our graph because remember the ball is moving in the negative direction. We've defined going downward as negative direction. So remember the ball started off with some initial velocity, and the velocity increased and it got faster and faster and faster as the ball was speeding up in the negative direction. So as we took this velocity time graph, we noticed that this velocity time graph gave us a rectangle here in green, and it gave us a triangle here represented in red. You guys remember what I told you? The area of a velocity time graph always tells us our object's displacement. So in other words, the area of this graph here represents the displacement of the ball from this point to this point right here. So this overall distance is the ball's displacement. So we're going to use that fact to derive this equation right here. I'm going to show you guys where this equation comes from. And this is the general equation for displacement. The displacement of an object is always equal to the initial velocity multiplied by the time interval plus 1/2 multiplied by acceleration multiplied by time squared. And so this is the equation that I'm going to be spending the next few minutes showing you guys where this equation comes from. Okay? So before we start deriving our equation, we have to start with the mathematical equation that we already know. And that mathematical equation is the definition for acceleration. If you guys remember what I told you guys, the definition of acceleration is equal to an object's final velocity minus an object's initial velocity divided by an object's final time minus initial time. Okay, so this is the mathematical definition of acceleration. So we're going to need to know this in order to ultimately get at this. So this is what we're trying to arrive at here. Okay, so before we ultimately get to this, I want to change the form of this equation just a little bit. I want to simplify it. And here's how I'm going to do that. If you guys remember the video, when we started taking our data points, we called this initial time, the first frame by which the ball fell, we called that initial frame or the initial time, time 0. So here's what I'm going to do. I'm going to plug in 0 seconds for this time in order to simplify this equation. So if I plug in 0 for the initial time, basically this part of the equation just goes away. And I'm just left with, some overall time interval that looks like this. So acceleration is equal to final velocity minus initial velocity, all of that divided by some time interval. Okay, so I didn't do much here. Just simplified this equation here to look like this by plugging in a time of t equals 0 seconds there. Okay. Now, there's something else I need to do here. You see this t here? I want to get this t out of the denominator here, and I want to move it over to the other side of the equal sign. And you guys know how to do that. From algebra, in order to get rid of this t here that's done in the denominator, all we would need to do is multiply the right-hand side of this equation by t. Okay, so if I multiply this by t, Notice I have a t at the top, and I have a t at the bottom. So this t will cancel out with that t. If you guys remember the rules of algebra, whatever I do to one side of the equal sign, I have to do to the other side of the equal sign. So if I multiply by t here, then I need to multiply by t here. And so this is what I'm left with. So acceleration times time is equal to an object's final velocity minus an object's initial velocity. Okay, so keep this equation in the back of your mind, because I'm about to get ready to start off a blank screen, but keep this in mind because we're ultimately going to need this in order to arrive at that. So I'm going to put a star there, and just let you guys know, again, keep that in the back of your mind, because I'm about to get ready to wipe this screen blank here, and we're starting off a new screen. But this is going to be very important in order to arrive at this, okay? Okay, so now we're ready to get to the main aspect here of this equation, and that is to figure out what is the overall equation for the displacement of an object. And remember what I said, the displacement of an object comes from the area of our velocity versus time graph. Okay, so let's start with this first. Okay, so let's start with the area of a rectangle. Okay, so look at this rectangle here in green. So the equation for an area of a rectangle, you guys should know. So the equation for an area of a rectangle is just this. It's just base times height, or height times base, however you want to see it. Okay, so that is the equation for the area of this rectangle here. Well, look at what we're plotting here. So what is it that we're plotting here along this height? In other words, what is the height of this rectangle from here to here? Okay, well, the height of this rectangle is nothing more but this point here. So if you guys remember, this point here, from this point represents the height of our rectangle. Well, what is that point? This point here is nothing more but the initial velocity here. So the height of our rectangle, in other words, the point from here to here, is nothing more but our initial velocity. Okay. So our initial velocity times our base. Remember, our base is the point from here to here. So the point from here to here is our base. What were we plotting along this base here? In other words, what were we plotting along this x-axis? Well, that's nothing more but the time interval. So our base is time. Okay. So that's the equation that describes the area of the rectangle. But what about the area of the triangle here in red? We can't forget this. What is the general equation for the area of a triangle? Remember what an area of a triangle is. An area of a triangle is 1/2 times base times height. 1/2 times base times height. That is the equation for the area of a triangle. Okay, so we're going to plug everything into our equation here. 1/2. Once again, what is the base here of our triangle? Remember, the base of our triangle is nothing more but this point here to that point there. Okay, so the base of our triangle, the length of this base, well, that's nothing more but our time in seconds here along the x-axis. So the base here is our time. So I'm going to plug in time. But what about our height? What about the height of the triangle? In other words, this length from here all the way to here represents the height of our triangle. Well, what is that? What is that length? Well, if you guys remember when we said, this point right here represents our object's initial velocity, right? Because remember, we started plotting here, and that's our initial velocity. And the points increase in this direction all the way to here. Okay, so here, and this point right here will be our object's final velocity. So that's easy. In order to find this height here, we just subtract this point by this point. So in other words, we subtract the final velocity minus the initial velocity. And this final velocity minus the initial velocity is equal to our height of our triangle. Okay? Now, remember what we said before. Remember that equation that we just looked at where I said that acceleration times time is equal to final velocity minus initial velocity? Okay, so remember this from the previous screen? Well, I have a final velocity minus initial velocity here. And I know what final velocity minus initial velocity equals. So all I can do, I can just take this here, okay, and plug it in there. So I'm just going to take this and plug it in for this because I know what final velocity minus initial velocity equals. And so this is what I get. I get 1/2 times time multiplied by acceleration times time. Okay, so all I did was just take this and plug this in here. Okay, now I'm almost done. I'm almost done here. Because if you notice, I have a t here and I have a t here. Okay, if I multiply t times t, that gives me t squared. So this ultimately reduces to 1/2 times t, 1/2 times a t squared. Again, I just multiplied this t times that t to get t squared. Okay? So this whole thing here represents the area of my triangle, and this thing right here in green represents the area of my rectangle. Okay? And I think you guys should see where I'm going with this. In order to find the overall displacement, all we will need to do is to add the area of the rectangle to the area of the triangle. So, and I'm going to do that now. So, the displacement of an object is equal to the area of our rectangle, which is initial velocity multiplied by time, plus the area of our triangle, which is 1/2 times acceleration times time squared. Okay? You know what? Let me do this in red here. So, okay. So the overall displacement of an object is equal to the area of our rectangle plus the area of our triangle, and there you go. That's our equation for displacement. So that's how you arrive at this equation. That's all you do. You just take the general form for the area of a rectangle as it relates to a velocity time graph plus the area of a triangle, and that is where the equation comes from, step by step by step. There you have it. Okay?